Hello, my name is Rotem Lehman. I am a master's student in Ben-Gurion University. My research supervisors are Professor Shani and Dr. Roni. The topic of our research is a partial disclosure of private dependencies in privacy-preserving planning. Collaborative privacy-preserving planning is a field where multiple agents need to collaborate in order to find a joint plan while preserving the agent's privacy. It includes private and public facts and actions for each agent. For example, in the rovers domain, there are multiple Mars rovers which are trying to collaborate in order to explore the surface of Mars by conducting several tasks, including taking photos of rocks and mining for minerals. In the following running example, there will be two Mars rovers, R1 and R2, that can access two base stations, B1 and B2. And they could use tools and sensors stationed in the bases, such as a camera, in order to explore a rock. So the sensors that are held by a rover and the rover's position are private. The private actions are movement actions. The public actions in this problem are the sensors located in bases and the current condition of the target rock. And the public actions are taking and returning sensors to the base stations, putting collected rock samples at the base stations, and performing various examination actions on rocks, such as taking an image, running a mineral, or collecting a sample. There is a well-known trade-off between privacy and efficiency in privacy-preserving planning. If you reveal less privacy in the planning process, you will result with less efficient plans. For instance, in the following plan, we'll show that R1 needs to do all of the work alone because R2 does not reveal any private information. So let's see the plan. You can see that R1 does all of the actions on its own, and R2 does not reveal any private information, so it does not participate in the plan. Sometimes revealing less privacy leads to not being able to solve a problem at all, or it could lead to finding a plan with a higher cost than the one with more disclosed privacy. On the other hand, revealing more privacy could lead to being able to solve the problems more efficiently. For example, the following plan will show that R2 reveals that it can take the pickaxe from B2 to the rock and mine the rock. This leads to a shorter plan with a Makespan of only 3 actions. Let's see the plan. So now they both share private information, so they both can collaborate together. But keep in mind that revealing it lets other agents know more private facts that revealing agent does not wish to share. Our main contribution in this article is to provide an experimental overview of the trade-off between privacy and efficiency in collaborative privacy-preserving planning. So now I will explain what is a private dependency. An action A is said to have a private dependency if it has a private fact F as a precondition such that one of the following holds. There is another public action A tag that after applying it and then applying some more private actions, we could achieve the fact F. For example, in order to take an image of the rock, R1 needs to take the camera from B1 and then drive to the rock. So let's see the plan. This is a dependency between taking the camera and taking an image of the rock, which are both public actions. Another thing that could happen is that F is either true in the start state or can be achieved from it by applying only private actions. For example, if R2 holds the camera C2 in storage at the start state, then it can drive to the rock and take a picture of it. So let's see the plan. Okay. This is a dependency between the start state and the action of taking an image of the rock. Instead of calling the private facts by its meaningful name, which is in this case holding R1 C1 and holding R2 C2, We have created artificial facts to represent the dependency without revealing the meaning of the private facts of the agent, such as F1 and F2 in this slide. Disclosing a private dependency does not mean to disclose the private fact, but it means that we reveal to other agents that we have a connection between one public action to another. And if we apply the first action, we could later apply the second. We do so by revealing that the first action can achieve the artificial fact that is a precondition to the second action. Our goal is to find a good plan while revealing a limited amount of private dependency. Our approach is to reveal k dependencies where k is a parameter, and then try to solve the problem with the revealed dependencies. The problem is how to know which dependencies should be revealed. For this problem, we have developed several heuristics in order to rank the dependencies by order of revealing. So in order to understand our heuristics, we have developed a directed graph that shows the private dependencies. The first column in the dependencies graph is a column of public actions that one or more of their effects lead to a dependency with another public action. The second column is a column of artificial facts, which are the facts that link between the public actions that have a dependency. Their names are obscured, so it will not reveal their meaning. The third column is another column of public actions. This time it is the actions that have a dependency as a precondition. And the fourth column is a column of public facts that are the effects of the public actions that we can apply using the dependency that was revealed. Another thing that you should notice in this graph is that the edges have a different role in each layer. The edges between the first and the second layers are edges that mean that each of the actions in the left side can publish the artificial fact in the right side. The edges between the second and the third layer mean that the artificial fact in the left side are preconditions of all of the actions that they are connected to. And the edges between the third and the fourth layer means that the action in the left side has all of the public facts it is connected to as an effect. Revealing a dependency means that we reveal a path between one public action to another via a blue artificial fact. As you can see, there are a lot of paths just like this one, so it is crucial to have a heuristic that will tell us which paths should be revealed. With the dependencies graph, we have created 4 heuristics in order to rank the dependencies in order for revealing. Each heuristics use a different aspect of this graph. Our first heuristic, which we denote M1, publishes artificial effects that are used as precondition in as many public actions as possible. As you can see, M1 would choose to publish F1, as it is a precondition to 3 public actions, while F2 and F3 are preconditions to only 2 public actions. The second method, which we denote M2, publishes an effect that enables the achievement of as many public facts as possible. An effect enables the achievement of a public fact F if it is a precondition to an action that achieves F. In our illustration, this is where there is a path from a blue private fact to a purple public fact. You can see that all of the artificial effects, all of the artificial facts enables the achievement of 3 public facts. So M2 would pick any dependency at the beginning. The third method, which we denote M3, attempts to maximize the amount of public actions that can be executed. That is, instead of publishing the artificial fact that provides a precondition for as many public actions, we publish the artificial fact that enables as many public actions as possible. You can see that F1 is the only precondition of take image rock1, and F3 is the only precondition of collect rock1. The other actions have more than one precondition, so they cannot be executed immediately. This will make M3 to initially reveal a dependency, including either F1 or F3. Our last method, which we denote M4, is similar to M3, but focuses not on the public actions, but on the public effects. That is, we publish an effect that enables achieving as many public facts as possible. You can see that F1 and F3 can both achieve one public fact, while F2 cannot achieve any public fact. This will make M4 to initially reveal a dependency, including F3 or F1. Okay. All of the heuristics are detailed in the article, but I will now present M3, which performed the best in the experiment in a more thorough way. As I said in the previous slide, M3 attempts to maximize the amount of public actions that can be executed. The first iteration, publishing the artificial effects F1 and F3, both enable immediately one public action. Assuming that we first select the fact F1, at the next iteration, F2 will now be able to enable the action mine mineral 1. In this method, which we also need to balance between enabling new public actions and enabling new ways to apply already possible actions. This may result in better plans. For each action A that is enabled by the published effect, we discount its score to be 1 divided by CA plus 1, where CA is the number of times that A was enabled by previously published facts. Hence, at the first time that an action is enabled, it provides a score of 1, at the second time a score of half, and so forth. So at the beginning, each action have a score of 1 because none were already enabled. If we indeed pick to publish F1 in the first round, then the score of take image rock 1 will be decreased to half, while the other actions will remain a score of 1 each. The red marked lines are preconditions that have been met for the actions. In the next round, the facts F2 and F3 will both be able to enable one action that have a score of 1. F2 could enable mine mineral 1, and F3 could enable collect rock 1. This shall lead to a tie between both facts. Assuming that we choose to reveal now the fact F2, then now the action mine mineral 1 will have a score of half, and the action sample mineral 1 will have an additional precondition met. That means that in the next round, M3 will have a score of 2, because it enables two actions which have not yet been achieved. So they each have a score of 1. Which means that F3 will be the chosen fact for the next round, and after revealing it, the score of both sample mineral 1 and collect rock 1 will be lowered to half. Okay, we evaluate our methods using benchmarks from the collaborative privacy preserving planning literature. We ran 2 planners with our different heuristics. The planners are the joint projection planner and the mass planner. For each problem in each benchmark domain, we first disclose no dependencies at all and then try to solve the problem. If we record if it was solved under a timeout of 5 minutes, and if so, we record the planned cost. We repeat the process disclosing new private dependencies, running the planner, and recording statistics. And then we compute the average solution cost and the number of solved problems. We will now show some results regarding the coverage of the different planners and try to answer the question of which heuristics performs the best. The following graphs show the coverage results on the joint projection method for the elevators domain. The x-axis is the amount of disclosed dependencies, and the y-axis is the amount of solved problems in the domain. The yellow line is the hindsight line. The hindsight is the amount of dependencies that were used in the final plan, where we have disclosed all of the dependencies. It is a baseline for comparing our methods. The green line is the line that represents M3. You can see that M3 performs the best for elevators. The purple line represents M4. In elevators domain, it performs the worst. The black line represents M1 and the dotted red line represents M2. In most domains, they perform very much alike, as well as in the elevators domain. In this slide, you can see the results of the four domains: elevators, logistics, rovers, and depots. The left side of the slide is results for the joint projection method planner, and the right side is for the maps planner. Notice that in all of the domains, M3 performs the best, and also notice that the joint projection planner solves more problems than the maps planner in all of the domains. As you can see in the elevators domain, for both the joint projection and maps planner, M4 performs the worst, and M1 and M2 performs very much alike. In the logistics domain, all of the methods perform the same. This is due to the domain having only one public fact for each action, causing all of the methods to choose the same dependencies to publish in the first dependencies, leading to a solution. In the rovers domain, the joint projection planner and the maps planner performs differently regarding the M4 heuristic. As you can see in the joint projection planner, M3 and M4 performs the same, while in maps, M4 performs worse than M2. In the depot domain, all methods performs much worse than the hindsight, leaving much room for improvements in this domain. We will now show some results regarding the cost of the final plans and try to answer the question of how revealing a dependency influences the final cost, the final plan cost. This table contains the average plan Makespan cost over the solved problems for each domain. Min denotes the average minimal cost over all solved problems. Min dep denotes the cost of the plan for when the problem was solved with the minimal amount of disclosed dependencies. Imp denotes the improvement between the first time that the problem was solved to the best achieved solution. I want to remind you the trade-off between privacy and efficiency that I've mentioned earlier. You can see the trade-off in the improvement column. When you publish less dependency, you receive a plan that has a higher cost. Notice that on average, the improvement is only 20% for the joint projection method and 10% for maps. This means that the cost of the plan found by the least amount of dependencies disclosed is close to the minimal cost that was found later. However, this varies in the different domains. As you can see in Bloxword, the improvement is almost 40% for the joint projection method, while in logistics it is only 6%. This happens in these domains because the Bloxword domain can be solved using one agent alone. So if we do not publish dependencies, then we shall have a higher cost than when we do publish dependencies and have a better collaboration between the agents. In the logistics domain, on the other hand, we have to collaborate. So the agents published the dependencies they needed for finding a plan. But when published more dependencies, they could improve their plan a little bit. So in conclusion, we have suggested the method for publishing only a part of the private dependencies between public actions of the agents. We have provided experimental results on the coverage and plan cost of the proposed method. We have shown that in many cases, a public plan can be computed with only a small portion of dependencies. And not only that we can reach a plan, it is also a good plan with a cost close to the best plan that was found later when revealing more dependencies. In the future, we plan to calculate the optimal set of dependencies needed for solving a problem. We also plan to use the privacy leakage analysis tool to confirm that when revealing less dependencies, you can achieve less privacy leakage. And we would also like to assign importance values to different dependencies. Thank you very much for listening.